Hello everybody, my name is Filip Rankavek and I will show you how to solve the first problem set from the Eigensolvers Quantum School. The problems were intended to provide you with or remind you basic mathematical tools, mainly from linear algebra, which are very important for quantum computing. So let's begin. The first problem involved checking whether a given vector is a plausible state vector. So let's remind quickly what does it mean. So if you have an arbitrary vector, okay, let's call its coefficients v1, v2 to vn, then we call it a plausible state vector if sum of squares of absolute values of its coefficients, which might be complex, which can have both imaginary and real parts, of course, if this sum is equal to 1. Okay? Why do we want it to hold this condition? Well, because the intended interpretation of these numbers, of these squares, are probabilities of obtaining these consecutive basis vectors in during measurement of the quantum state described by this vector, right? So if a vector holds this condition, we know that it describes some quantum state. Okay, so we just want to check whether these vectors satisfy this condition, right? So the first one is 1 over square root of 2, 1, 1, right? So we can check that it in fact satisfies this condition, because these squares are just two halves which sum up to 1, right? So it is a plausible state vector. We also call it a normalized vector. But in the second case, it is a very similar vector which has another factor in front of it, right? Here is 1. We can write this one, doesn't change anything, but it is not 1 over square root of 2. So by only this, we already know that it is not normalized, because it's another factor. In fact, it's 2. I mean, the outcome of our formula is 2. So to normalize this vector, okay, we have to divide it by a square root of this number that we got here. So by 1 over square root of 2. So we get the same vector as we had in the first example. So these two first examples didn't involve any non-real numbers. So the absolute values were just classical absolute values as we know it from elementary school, right? But now we have a vector which has as coefficients 3 plus 2i, 0 and 3i. So as a reminder, if we have a complex number which has alpha and beta as their real and imaginary part, then absolute value of such a number is square root of alpha squared plus beta squared, okay, where alpha and beta are real. So that's the formula, and we can just simply check that this vector doesn't satisfy our condition. Okay, because it's 22, right? So to normalize it, we have to divide it by square root of 22, as before, as previously. And that's it. Okay, and now we have not just a vector, but a matrix multiplied by a vector, right? It can be interpreted as a quantum gate applied to some quantum state, by the way. Namely, this matrix is a poly Y matrix, right? So we can compute the vector first, right? 1 times 0 and minus I times 0 is 0, and here it is I. And now we can compute our formula. So it's 0 squared plus I squared. So it's 0 plus 1, right? So it is a plausible state vector. We don't have to normalize it. Next one is a bit tricky because we have an infinite vector whose coefficients are whose coefficients form a geometric sequence. Each number is the previous one, but multiplied by each of these numbers is a previous number multiplied by 1 over 2, right? So we can plug these numbers to the formula. And we will see that it's a geometric sequence. Here we can just leave these absolute values because all these numbers are positive reals, right? So taking absolute value doesn't change anything. So let's write 1 plus 1 over 2 squared plus 1 to 2 times 2 and so on. In fact, it's sum of 1 over 2 to 2i. Well, we start with I equal to 0 and we go to infinity. So it's a geometric series whose factor is 1 over 4, because we multiply by 1 over 2 squared each time, right? So it's 1 over 4. So we can compute, and of course it's smaller than 1, so this series converges to some number. So we can compute this series as 1, because that's the first term, over 1 minus 1 over 4, right? So it's 4 over 3. And that means that it is not a plausible state vector, because this whole number doesn't equal to 1, but we still can normalize it, right? So let's do that maybe here, that we can divide the whole vector by square root of this number, right? So it will be square root of 3 over 2, right? Because square root of 4 over 3 is 2 over square root of 3, right? So it's square root of 3 over 2. And that's the normalized vector. Now for the second problem. We have to find Hermitian conjugates of these matrices. So maybe I will quickly remind you what a Hermitian conjugate is. If we have a matrix M with entries A, I, J, where I and J are some indices from 1 to some natural number n, okay, then a Hermitian conjugate of such a matrix, which is denoted with this little dagger here, is matrix with coefficients a, j, I. Okay, so with these coefficients conjugated. Okay, because these can be complex numbers, and they are conjugated here, and also this matrix is transposed. That's why here is these indices are ij and here ji. So it is transposition plus conjugation of entries of conjugated entries, right? This is how you can think about it, right? We transpose the matrix and conjugate entries. So let's just do that for these matrices. Okay, so the first one is 0, minus I, 0, I, 0, I, 0, I, and 0. Okay, and maybe a quick reminder that when we have some complex number with real part alpha and imaginary part beta, then its conjugate is just alpha minus beta I. Okay, we just put minus before beta, and also a transposition is just transformation of a matrix such that rows become columns and vice versa. So we take this first row and write it as a first column, right? So it's 0, and also we conjugate these entries. So 0 conjugated is just 0, right? Because it has only this real part, which doesn't change. But I, minus I conjugated will becomes just I, right? Because there is this minus sign before this the imaginary part, and 0 is 0. Okay, and we take a second row and make it a second column. So it's minus I, 0, minus I. And here the same, 0, minus I, 0, right? And that's the answer to the first question of this problem. The second one is a quite big matrix. It's 6 by 6 matrix, but observe that these numbers, these all entries of this matrix, are real numbers, right? If we have a real number, its name already tells us that it has only the real part, so it has no imaginary part. So there is no imaginary part to put minus before, right, in front of it. So it doesn't change. So conjugate of each real number is just itself, right? So I won't write all of these entries. I won't write the whole matrix, only the first row. Okay, so the only thing we have to do here is the transposition. We just have to transpose this matrix. So these rows become columns, right? All these rows become columns here, but the entries, these numbers, don't change, right? Because we have only this alpha, this real part, and it stays the same. Okay. The next one is a row vector, I, 0, 3 plus 2i, 5i. So the outcome will be a column vector, right? Okay, I don't have spare place here. Maybe I will clear it here. Okay, so C dagger is minus I, right? 0, 3, minus 2i, and minus 5i. I conjugate all the numbers. That's the answer. And now we're going to check whether a given matrix is unitary. So what does it mean? If we have a matrix M and we multiply it by its Hermitian conjugate, and it turns out to be a unit matrix, okay, which is of course a matrix of the form such that on a diagonal we have ones and everywhere else we have zeros, then we call such a matrix unitary. In other words, its Hermitian conjugate is its inverse, okay? Because multiplied by the former matrix, it gives a unit matrix. So we just have to compute Hermitian conjugates of these matrices and find out whether the product of this matrix and its Hermitian conjugate is a unit matrix. Okay, so the first one is 1 plus I, 2 minus I, 3 plus I, and 4 minus I. Okay. And its Hermitian conjugate is 1 minus I, 2 plus I, 3 minus I, and 4 plus I. Okay, so that's the product we are going to compute. And actually what is worth observing here is that equivalently we can talk here about condition whether these rows are normalized vectors, right? Because you probably know that if we have a complex number and its conjugate, and we take their product, it turns out to be absolute value squared of this number, right? So actually, when we compute numbers on the diagonal of the resulting matrix, okay, because we get some matrix here, and we compute what is here at these places, right, on the diagonal, we want them to be ones if this product is unit matrix, what is our condition, and it means that sum of squares of absolute values of these numbers is 1, right? So it is the condition that we had in the first problem, that that this row is a normalized vector, right? Because pay attention to that, when we have this number, we wrote here its conjugate, right? And similarly here and here, right? So if we multiply them, right, to get this number that is here, we get absolute values squared of these numbers, right? So here it is absolute value of this number is 2, okay, plus absolute value of this number, it is 2 squared plus of course I'm talking about absolute value squared. It's 2 squared plus 1 squared, so it's 5, so it's 7, so it is not 1. So this matrix A for sure isn't unitary, okay? Of course it is not a sufficient condition for a matrix to be unitary that its rows are normalized vectors, because we also need other entries of the product matrix to be 0, right? That these rows are also orthogonal, that product of different rows are zeros. Okay, so let's go to the next, and the next example, in fact, satisfies both conditions I talked about, because all its rows have because all its rows are normalized vectors, right? Because its entries are zeros and single ones. So we already know that sum of squares of absolute values are ones in each case, and also dot product of each pair of these rows is 0, because these ones are just placed on different places. You know what I mean, that if we multiply any of these row vectors, okay, I mean, if we take a dot product of transpose of one of them with another, with any one of the I mean, if we take a dot product of transpose of any of these row vectors with any other row vector, okay, we get 0, just because we have only one in each of the columns, right? And that's why we can say that this matrix in fact is unitary. Okay, and the last one is a little bit more complicated, and actually it uses some specific representation of complex numbers, which is called Euler's form. And as you probably know, it works this way, that we have alpha here, that if we have alpha and e to e phi, where alpha is some real number as well as phi, then its absolute value is absolute value of alpha, okay, and conjugate of such a number is alpha e to minus I phi, okay. Namely, alpha is absolute value and phi is argument of this number. So we can compute this product to check whether it's a unit matrix or not. So here we have to plug in the Hermitian conjugate of this matrix. So it's cosine theta over 2, right? Because it's some real number. If theta is real, what I guess we have to assume. And here we have this minus, okay, before I lambda, and sine remains unchanged because it's just the absolute value of this number. And here we get minus before I phi and sine theta over 2, and here e to minus I phi plus lambda cosine of theta over 2. Okay, and take a look that when we multiply this row by this column, we get sum of squares of absolute values of these numbers, right? That's what I was talking about in the previous example, right? Because we multiply these numbers by their conjugates, okay? So we can take just absolute values of these numbers and square them. So it's cosine squared theta over 2 plus, and here the absolute value is just sine of theta over 2, right? So it's plus sine squared theta over 2. But from trigonometry, we know that it's equal to 1. So we have 1 here. And similarly, here will be 1 as well, because we multiply this row with this column, and absolute values squared of these numbers are sine squared plus cosine squared, right? So it's 1 as well. And what remains to check is whether these numbers that lie here are zeros or not. So we have to multiply this row with this column. So it's let's do it here. Right, we multiply it. Okay, cosine theta over 2 times e to minus I phi sine. Oh, it's minus actually. And we can factor out cosine theta over 2 times sine theta over 2. And here we have e to minus I phi times, oh okay, minus e to minus I lambda minus I phi minus I lambda. So here I lambda just cancels out, right? And we get e to minus I phi minus e to minus I phi, so minus the same number, and that's why the whole thing is 0. So here is 0. And very similarly, if you compute product of this row vector with this column vector, you get practically the same formula, which is also 0. So the resulting matrix is a unit matrix, what means that C is a unitary matrix. And that's the answer to this example. In the fourth problem, we want to find eigenvalues and eigenvectors of some matrices. So let's remind quickly what eigenvalues and eigenvectors are. If we have a matrix M and there exists some vector that this matrix scales up by some constant vector lambda, we call lambda its eigenvalue. And the corresponding vector is eigenvector. Actually, for each eigenvalue, the many eigenvectors, which we will find out in these examples. So the first one, C, is 7, 3, 3, and minus 1. And to find eigenvalues, we want to find a determinant of such a matrix, C minus lambda times unitary, time C minus lambda times unit matrix. Okay. Okay, so it's that 7 minus lambda, 3, 3 minus 1 minus lambda, which is 7 minus lambda, 1 minus lambda, minus 9. Okay, and this is lambda squared. Minus 6 lambda, minus 7, minus 9, so it's minus 16. Okay, and this is some lambda minus. So this is a polynomial of second order, so there are two roots, and these roots are, well, it will be 2 and 8 with okay, plus here or plus here, because you see that 2 times 8 will give us 16, but we need plus somewhere to make it minus 16, and we want it to give us minus 8 plus 2, right? Okay, minus 8 lambda plus 2 lambda gives us minus 6 lambda, and lambda times lambda gives us lambda squared, of course. So lambda 0, which is the first eigenvalue, is minus 2, and lambda 1 is 8. Okay, so we found eigenvalues of this matrix. Now we want to find eigenvectors corresponding to these eigenvalues. So to do that, we just write the formula, this formula, for our data. By this I mean that this matrix times some unknown vector, let's call it xy, gives us, okay, I will write that lambda 0 is -2 and lambda 1 is 8, right? And this is -2 times xy, right? This gives us some system of equations. So it's 7x plus 3y and 3x minus y. And here we have -2x and -2y. And it turns out to be that 3y equals -9x, and here minus I equals 3x, right? So we see that any vector such that y equals -3x, right? We can, of course, here put this minus here, and here we can divide both sides by -3, or by just by 3, right? And we get -3x. So corresponding eigenvectors are of the form 1, or maybe some x and -3x. Okay, so it's like the simple form is 1 minus 3, where we can, I mean, the form with x in front of the vector. If your outcome was something different, but multiplied by some constant factor, then it's also good, of course, because this x can be anything. Okay, and let's find the same, but for the second eigenvalue, which is 8. Then we have 7, 3, 3, and -1 times xy equal to 8xy, right? And we get a system of equation corresponding to this eigenvalue. And now we get that 3y equals x, and 3x, or maybe y, 9y equals 3x. So now we get that x equals 3y. So we can write it as maybe here. We write this as x equals 3y, right? So we can write y here and 3y here. So we get some 3 and 1 and y in front of this vector. So this is the general form of eigenvectors for this eigenvalue. Okay, and the next one is 4 square root of 3 square root of 3, 2. Right. So we do the same. Determinant of b minus lambda times I, which is 4 minus lambda, here 2 minus lambda, and square roots of 3 without any change. And this is 4 minus lambda times 2 minus lambda minus 3, right? So we have lambda squared minus 6 lambda plus 8 minus 3, so it's 5. And here, as previously, it's we want to find roots, so it's lambda minus 1 and lambda minus 5, right? Because when we multiply minus 1 by minus 5, we get 5, and minus 1 lambda minus 5 lambda gives us minus 6 lambda. Okay, so lambda, maybe here lambda 0 is 1, Okay, and lambda 1 is 5, right? And now we want to find eigenvectors. Okay, 4 square root of 3 square root of 3, 2 times some unknown vector equals xy, right? Because multiplying by 1 doesn't change anything. So we have 4x plus square root of 3 times y equals x, and square root of 3 times x plus 2y equals y. And now we obtain that 3x equals minus square root of y, and here okay, I'm just thinking about what is better. Is better writing y as some function of x, or the other way around? By the way, it doesn't matter, we can do both things. What changes is just simplicity, but let's do this way when we started. Oh, okay, it's maybe better. Minus y, and we get that x is just minus 1 over square root of 3 times y. Yeah, maybe the other way around would be better. I mean, it's more elegant to write y equals minus square root of 3 times x, but this one also works. It's the same, right? So we can write this vector as 1 minus square root of 3, right? With some constant factor in front of it. And now we want to find the second vector, the second eigenvector. So now it's 5 times x, y, right? So it's a bit different system of equations with different solutions. Okay, and it's square root of 3 times y equals x, and here it's minus 3y equals minus 3x. Okay, maybe this way. And we see that x, this time x equals square root of 3 times y, right? So this vector is some okay, one here y, and here it will be square root of 3, right? Because x equals square root of 3 times y, and that's the general form of this of these eigenvectors. What's the next one? Okay, and now we have a matrix that represents a Hadamard gate, what some of you may already know, and it's 1 over square root of 2, 1, 1, 1 minus 1. So let's compute its eigenvalues. Okay. Here we see that it will be difference of squares, right? So we can write it as wait, it's square root here, right? So we can write it as half minus lambda squared minus 1/2, and it equals lambda squared minus 1. Okay, so it's lambda minus 1, lambda plus 1, right? So eigenvalues are minus 1 and 1, right? Now we can find eigenvectors. As previously we have some system of equations, I propose to multiply the whole thing by square root of 2, okay, both sides. Then we will have some simpler form of this system of equations. So we get x plus y equals minus x times square root of 2. And x minus y equals minus y times square root of 2. That's the second equation. What we get is y equals minus actually minus x 1 plus square root of 2. Okay, and here we get y times minus 1 plus square root of 2 equals to minus x. In fact, we get here from the second equation that y equals 1 over square root, no wait, 1 minus square root of 2, right? Because of this sign, we multiply this by minus 1 times x. So what is worth of noticing, these numbers are equal, okay? What might not be clear at the first glance, because when we multiply this number by 1 plus square root of 2 over 1 plus square root of 2, which is 1, right? Because these both numbers are the same. We get 1 over 1 plus square root of 2 over some difference of squares, right? It's 1 minus 2, right? Because 1 squared minus square root of 2 squared, which is 2. So it's minus, maybe there's no empty space, so I'm gonna clear it. So it's minus 1 here, and it's minus 1 plus square root of 2 in brackets, and that's why this number is equal with this one, so it's not a contradiction. And we get our first eigenvector, which is 1 here, x, and minus 1 plus square root of 2, right? And for the second one, now the right side of the system of equation will be just xy, because we have eigenvalue equal to 1. So it's x plus y equal x square root of 2, x minus y equal to y square root of 2, and this gives us something very similar, probably, because it's square root of 2 minus 1, and here we get y equal to x times 1 over, actually there will be minus 1 plus square root of 2, okay? And similarly, I won't do that for this one, but again, we can check that these numbers are equal, and we get our second eigenvector, which is x 1 and square root of 2 minus 1. Okay, I hope that's clear. Okay, now we want to calculate such a sum. So as you probably already know from the first lecture, these products of cat first and bra second are some operators. So probably the outcome of such a sum will be some matrix. That's what we can expect. And, well, this is just, we start with 0 and go to 1, right? And here the same. So it's just 0, 0, plus 0, 1, right? And then plus 1, 0, and plus 1, 1, right? Yeah, because we start with 0, yes, then go to 1, and with j the same, 0, 1, 0, 1, okay? And now we want to check what kind of matrix this actually is, right? So recall that this vector is actually, in the computational basis, it's 1, 0, right? And if we take bra, so we conjugate it, it's a row vector, it becomes a row vector, right? And similarly, 1 in the computational basis is 0, 1, and this one is 0, 1, but in a row form. So we can just plug it here. So it's 1, 0, and here 1, 0, plus 1, 0, and here 0, 1, and so on. So now we have 0, 1, and 1, 0, and plus 0, 1, and 0, 1, right? And now we just need to do the multiplication. So we take a row and multiply it by columns, right? So a row is 1, and times 1 is 1, times 0 is 0, 0 times 1 is 0, times 0 is 0, right? We get our first operator, our first matrix, and the same here. 1 times 0 is 0, 1, 0, 0, and so on. 0 times 1 is 0, 0, 1, 0. And here, 0 times 0 is 0, 0, 0, and 1, right? And the outcome that I'm gonna write maybe here, okay, here will be the outcome of this sum, is of course 1, 1, 1, 1, because we sum all these matrices. And that's it, that's the answer. Okay, the last problem involves some formula that allows us to compute products of Pauli matrices. And this formula uses something that's called Levi-Civita symbol, okay, as well as Kronecker delta. Kronecker delta actually checks whether two numbers that are given as inputs, that's how we can think about it, whether these numbers are equal or not. And Levi-Civita symbol checks the order of three numbers that we gave it. So maybe I will show it. How does it work on the side? So Kronecker delta equals 0 or 1. Okay, 1 if these numbers are equal, and 0 if they're not equal. Okay, and because in this problem we have to check three cases in which all these indices are different. In each case, this delta will be equal to 0. Yes, because we have to check cases in which these indices are x, y, y, z, and x, z, right? If we would have to compute the case in which we want to compute a product of sigma x with sigma x, then this delta would be 1. Okay, so we can just we can just forget about this part, okay, because it will be equal to 0. We just have to compute this sum. So what is this Levi-Civita symbol? So it checks whether these symbols are in a clockwise order or anti-clockwise. We can just show it, I think, with 0, 1, and 3, because 0, 1, and 2, because that's what we will deal with. So if they are given in this order, okay, then it's equal to 1. Okay, if clockwise. That's one of the ways that we can think about it. I think you can think of this you can think about it in the terms of clockwise and anti-clockwise, and it's good to visualize. Oh, 0. Sorry, excuse me. -1, not 0. -1 if anti-clockwise. Okay. And 0 if none of these. None of the above, right? So in other in other cases. So if we have, for example, maybe this is anti-clockwise, right? So anti-clockwise. Okay. So if we have, for example, 0, 1, 2, then the symbol is 1, right? If we have I don't know, 1, 2, 0, it's also 1, right? Because 1, 2, 0, it's clockwise. But if we have 2, 1, 0, okay, it's 2, 1, 0, we go anti-clockwise, so it's -1, right? If we have 1, 1, 0, it's none of these, right? Because one of the symbols repeats, so it's 0. And that's all. That's how it works. Okay, now I'm gonna also write down these Pauli matrices, okay? It's -I here, right? I'm gonna check it, but I think it's correct right now. Wait. No, it's not this way. It's this way. Yes. Okay. And we can just compute these products. Yeah. Also, these indices correspond to these matrices as this is the first one, this is the second one, and this is the sorry, this one is 0th, this one is the first one, and this is the second one. Okay, and okay, now let's take the first one. So let's write it this way. Okay, so we have I, some sum, and K, which can be 0, 1, or 2, right? But pay attention to that. If any two indices in this symbol repeats, then it's 0, right? So we can neglect those cases in which K is one of these, right? So we only care about K different from 0 or 1, right? So it's not a sum, it's just one element, right? Because only 2 is left. So we can write it as epsilon 0, 1, 2. And here will be sigma 2, so it's z. 1, 0, 0, -1. Also, we have to remember that this I is an imaginary unit, not one of indices, okay? That's a little collision of this notation. And we get I, 0, 0, -I. If we actually multiply these two matrices, we will find out that this is the correct answer, right? Because we multiply this row by this one, we get I. This row and this column are orthogonal, so we get 0. Similarly here, and here we get 1, 0 times minus I, 0. Yeah, so this formula works, at least for this example, but we know from other sources that it works for each of cases. So now we can compute xz, for example, okay? So it's I times, and again, only one case isn't 0 for this epsilon, for this Levi-Civita symbol, okay? So it's, now it's 0 and 2, okay? So maybe I will write it, because it should be written this way, right? And then we don't have these indices here. So it's 0, 2, and 1, okay? And this is actually in anticlockwise order, so it will be minus 1, right? And times sigma 1, right? So it's y. So it's 0 minus I, 0. And it is minus I, 0 minus I, 0, right? So it is, here we have minus 1, because I times I is minus 1, and here it is plus 1, because we get this minus sign as well, and it is 0. So that's the answer. And we can also do the last one, which is yz. Yeah, I will quickly check, are these the cases that we are supposed to do? Yes, so this is the second one. Okay. And this will be I times epsilon. This is 1, 2, and 0. And this one is a clockwise order, right? So it will be 1, and times 0, 1, 1, 0. So it's gonna be 0, I, 0. Okay, that's the answer. So I hope you've done it correctly. If not, I hope that you understood how to do that. And now the bonus problem. This is the first problem where we have any quantum gates. This is the Hadamard gate and CNOT gate, which are given here as quantum operators with plus and minus states and 0 and 1 from the computational basis. So they are defined by what they do to the basis vectors from the computational basis, right? So as you see, this notation that h equals plus 0 plus minus 1, it actually means that this operator applied to zero state, right, from the computational basis, it gives us an output plus state, okay, where plus is something like that. Written in computational basis is 1 over square root of 2 times sum of 0 and 1, and minus is the same but with minus instead of plus. So if we apply h to 0, it is just plus. So because these two vectors 0 and 1 are orthogonal, this one cancels out, right? Because this dot product is 0 and this one is 1, right? So what survives is plus. Okay, so this notation, it's good to read it as 0 goes to plus and 1 goes to minus. And very similarly in the CNOT case, but here this notation tells us what CNOT does to a pair of qubits. Okay, so it transforms 0, 0 to 0, 0, 0, 1 to 0, 1, but 1, 0 to 1, 1, and 1, 1 to 1, 0. Okay, so we can just compute what the resulting state of this circuit drawn above does. So we start with 0, 0 state, right? Okay. So we start with 0, 0 state here, right? And first we apply Hadamard gate to the first qubit, and then we apply CNOT to the resulting pair of qubits. So let's compute first what is the first qubit here. So H0 is, of course, that's what I showed to you. That's what I written down previously, and I cleared it, but it's plus, right? So you've already seen it, and the resulting pair is plus 0, right? Before CNOT applied. So we can write it as 1 over square root of 2, 0, 0 plus 1, 0, right? And CNOT of this is, maybe I will write it here, and I should write it here, somewhere here, okay? CNOT, forgive me this terrible notation, but you know that CNOT is applied here and here, because each operator in quantum computing is linear. We can split it into each part of this sum. Okay, and now we can just write this whole formula, but it will be non-zero in only one part. So we can apply here this 0, 0, okay? So it will be something like this. We will have these dot products everywhere, but pay attention that here it's 0, right? Because these states are orthogonal. Here it is 0 as well, and here it is 0 as well. So what only survives is this part, which is 1, okay? And we get this 0, 0, right? What does make sense, because CNOT changes the state only if the first qubit is 1. And similarly, we can get from this part that we get here 1, 1, right? Because this dot product will be non-zero only in this place, so it will give us 1, 1, right? So the resulting state is 1 over square root of 2, 0, 0 plus 1, 1. That's the answer. And the second part of this problem was to separate a non-separable state. So as you probably know, this state cannot be separated as it is proposed here, suggested here, and thus any one of you who sent us their solution won't get this prize, so forgive us. It was just kind of a joke which was supposed to give you knowledge about that this state, which is called Bell state, cannot be written as a tensor product of two states. It's a very important kind of quantum states, and it's called, this type is called entangled states. And that's all for now. Thank you for watching this video. I hope you learned something new or confirmed your beliefs about solutions of these problems. If you have any further questions, just feel free to ping me or any one of other mentors on Discord, and we will help you out if you're stuck on any of these problems. And see you soon in following videos. Bye.